Welcome back. In our introductory lecture, we took a look at what chemistry is, and we saw that chemists really study everything. But what distinguishes our science isn't what we study, but the scale on which we focus when we make our observations. And what an unusual scale it is. Atoms and molecules are substances that collectively make up practically every piece of matter that we will ever encounter, but which individually are so minuscule that they defy direct observation. They are simply so small that we will never truly see one atom or molecule directly with our own eyes. But we have many other tools to make these observations with, developed over the last few centuries for the most part. In recent decades, it's actually become possible to measure the physical features of atoms and molecules. But the chemist's commitment to this tiny scale creates a few problems, not the least of which is that when you change your focus from objects in your everyday world to that of atoms and molecules, the scale changes so drastically that the usual methods of measuring fundamental properties of an object, like its length or its weight, simply fall short. As a general rule, scientists are just like any other people. We don't like to waste our time. We don't want to work with cumbersome numbers that have many leading or trailing zeros. Now, what if we need to compare two values that are drastically different from one another? It'd be helpful if we had a method of writing some of those cumbersome numbers that I pointed out earlier. Try mentally comparing a trillion to a trillionth. It takes some real mental gymnastics to get even a rough idea of the difference in scale of these two numbers, let alone an exact ratio. The problem that we run into is that considering processes over huge differences in scale often leads to situations just like this. The situation is one in which values span many, many orders of magnitude, but we have to compare them. So how do we cope with this as scientists? Well, we use a very special type of notation in our numbers called scientific notation. Let's consider a few very simple numbers that differ widely in scale. A billion, a trillion, and a quadrillion. Numbers that you're probably relatively familiar with. Now, a billion, a trillion, and a quadrillion, of course, each have quite a few zeros after them. And those zeros aren't doing much except conveying the size of the number. And so, if we can find a way to convey the length of that string of zeros at the end in a more efficient fashion, then we'd like to do that. Now, a billion is followed by 9 zeros. A trillion would be 1 followed by 12, and of course a quadrillion would be a 1 followed by 15 zeros. So how can we convey in a more compact fashion the number of zeros trailing that 1? Well, what we do is use an exponent. So in this case, 1 billion becomes 1 times 10 to the 9th, where the 9 in our exponent conveys the number of zeros trailing the figure that we're interested in. Similarly, 1 trillion can be written as 1 times 10 to the 12th, and 1 quadrillion can be written as 1 times 10 to the 15th. Now, this sort of treatment also extends to very, very small numbers. For example, a billionth, a trillionth, and a quadrillionth. Very, very small decimals in which there are meaningful numbers at the end of these, but there are long trails of zeros leading them that do nothing more than convey the magnitude of the number. So once again, we want to find a way to condense that magnitude into a simpler expression. So when we have 10 to the minus 9 versus 10 to the minus 12 versus 10 to the minus 15th scales, we simply include those in the scientific notation. A billionth becomes 1 times 10 to the minus 9. A trillionth, 1 times 10 to the minus 12. And a quadrillionth, 1 times 10 to the minus 15. So scientific notation can help us by condensing the scale of large numbers down to an exponent. That makes it easier to look at. Now that can be, and will be, very useful as a tool for expressing numbers as we go forward. But a number alone is not a value. Let me give you an example. I'm 74.0 tall. That's a very specific number, isn't it? But 74.0 what? Inches? Millimeters? Miles? By now you can see my point. The number alone does not convey a value. It's the number in combination with a unit that truly gives us valuable information. If I omit the unit, the value is lost. So numbers and their units combine to convey values. Now, in theory, as long as we choose the proper unit to go along with the proper number, a value can be reported in multiple ways. I am 74.0 inches tall. That's 6.17 feet, 188 centimeters, or 2.06 yards. All of those combinations of numbers and units convey exactly the same value of height. So numbers and units properly paired up help us communicate values. But not all units lead to very understandable conversations. Imagine a coworker going about his or her day discussing her 1/1,000,000th of a light-year commute to work that took a whole 20 minutes today because of a traffic jam. Or the man behind the counter at the candy store selling handfuls of jelly beans for 110,000 cents per metric ton. It's hard to imagine the exact values involved, isn't it? A 1/1,000,000th of a light year is a very specific distance, and 110,000 cents is a very specific amount of money. Each is a very well-defined value. But reported this way, these values are simply difficult to understand because those numbers are so large and so small that our minds can't get wrapped around them easily. Our commuter was upset because 6 miles took 20 minutes. Our vendor's candy price is $2 per pound. Much more easily understood when we use appropriate units. Chemists have taken this strategy as well, when scientific notation simply won't do. We create new units of measurement that produce easily handled numbers on the scale of atoms and molecules. So let's think about a few common measurements of matter that we might need to describe them on scales so small or otherwise unusual that common everyday units of measurement just won't get the job done. Let's start at the beginning with one of the simplest units of measurement that we can imagine: length. Simple though this measurement may be, measuring lengths or distances as accurately as possible is crucial in chemistry. When it comes to the positions of atoms and molecules, fractions of nanometers, distances less than 1/1,000,000th of the width of a human hair can make a difference. Most of us are familiar with the metric system's standard unit of length, the meter. I myself stand nearly 2 meters tall, and there are more than a few atoms making me up. So you might imagine that when we try to describe distance in atoms and molecules, meters are going to lead to some pretty small numbers. So small, in fact, that we don't ever really report these kinds of distances in meters. In fact, a typical atom is about 1 × 10⁻⁻10 meters across. Remember, that's a decimal with 9 zeros after it before the 1. Scientific notation is one solution. But instead of working with awkwardly small numbers like this, we more typically use one of two strategies. First, we can use metric prefixes to pare this meter down close to the size of an atom. 10 to the -10th meters becomes 10 to the -7th millimeters, which equals 10 to the -4th micrometers, which equals 0.1 nanometers. We might even choose to say 100 picometers. Finally, we're getting to a point at which the numbers we have to use to accompany those units aren't so cumbersome or awkward. The second strategy is to create our own customized unit, tailored to be used in measuring distances at the atomic scale. Chemists have also done this, designating a length of 100 picometers, or 10 to the -10th meters, with a name all its own: angstroms. It's a unit named in honor of Anders Jonas Ångström, and it's indicated by a capital letter A with a ring diacritic as a testament to his Swedish roots. So, using angstroms, the size of atoms and the bonds between them can be expressed in digits close to 1, simplifying the reporting process. A typical carbon-carbon bond, for example, like the ones helping to hold your DNA together or storing a great deal of the energy in a tank of gasoline, is about 1.5 angstroms long. Of course, you can't talk about matter without talking about its defining characteristic: mass. All objects have mass, even atoms. But just as we did with lengths, we run into a tough situation when it comes to reporting the mass of atoms and molecules. They're simply too small to use conventional units easily. Weight and mass are, of course, very important related pair of properties. Larger objects, like a person, can be weighed to determine their mass. This is because Newton's law of gravitation tells us that the Earth pulls downward on us, all with the same force, making our weight and our mass proportional. But molecules and atoms are just too small for this kind of treatment. We can't weigh a single molecule or atom like we can a larger object. Chemists do have ways of determining the masses of atoms and molecules, and we'll get to those techniques a bit later in the course. But for now, consider this. I weigh about 190 pounds. Fine, 195 today because my wife baked cookies last night. Either way, I get a manageable number when I step on the scale. But an atom of carbon weighs 4.4 times 10 to the minus 26th pounds. That's a decimal, 25 zeros, and 2 fours in front of our pound unit. That is not a manageable number. And we can't get it higher by feeding the atoms cookies either. So, chemists use a different unit altogether to report on the mass of atoms and molecules. A unit called the atomic mass unit, or AMU for short. As early as 1850, scientists were using this special unit to communicate the mass of a single atom of one type in comparison to others. Its original definition is 1/16 of the mass of a single oxygen atom. Now that might seem a little bit unscientific, right? Setting a standard for mass based on oxygen atoms. But it turns out that when you set the mass of an oxygen atom to 16, the mass of a hydrogen atom, the smallest of them all, is equal to about 1. Oxygen was used as the standard simply because its natural abundance in our environment causes it to appear in so many naturally occurring materials. To explain how the atomic mass unit itself is defined in modern times is going to require that we discuss the structure of the atom, which we're going to do very soon. But for now, just as in 1850, it's a fine working definition for us to say that it's about equal to the mass of a single atom of hydrogen. How convenient. Hydrogen atoms are about 1 angstrom wide and have about 1 atomic mass unit worth of mass. Oxygen atoms have 16 mass units. And these numbers are a lot easier to work with. We're making really good progress here. Next, let's consider another simple value, quantity. In many situations, we measure collections of discrete objects, not by their mass, but simply by the number of those objects present. For example, we usually buy eggs by the dozen, 12 at a time. Rarely do we buy eggs by the pound. Now, sometimes this kind of measurement is also important to chemists. For example, when atoms interact, bond, and undergo chemical processes, it's often in whole number ratios of atoms, not their masses, their amounts. So many times it becomes critical to be able to report on a number of atoms in a certain sample, rather than the weights or mass of that sample. But this presents a real problem. Atoms are small. So small that chemists had to devise all new units of measurement just to report on their dimensions and their masses without driving themselves crazy. Now try this one on for size, no pun intended. 1 pound of gold, 16 ounces, would contain more than 1 trillion atoms. That's a 1 with 24 zeros after it, 10 to the 24th. These numbers are a staggering testament to the incredibly small size of atoms. These numbers are also so large that they simply aren't worth dealing with. So once again, chemists have created their very own unit for counting atoms, much like a dozen might be used to count eggs out at the store. But chemists' counting unit is much, much larger. And the consensus quantity is 602 billion trillion, or a 6 with 23 zeros after it. 6.02 times 10 to the 23rd. We commonly call this counting unit a mole. A mole is a difficult quantity to visualize. Because atoms are so very, very small, a mole is a very, very large number, thus allowing us to count atoms using numbers that don't boggle the mind. A mole of marbles would be enough to cover the entire surface of the Earth to a depth of several miles. A mole of human steps would cover enough distance to cross the Milky Way galaxy 500 times. A mole of dust mites weighs about 300 quadrillion metric tons. And a mole of human beings would have the mass 10 times greater than that of the planet Earth. So, a mole is big. It's really big. But why this number? Why not something nice and round? Well, the answer there lies in proportionality. Remember that oxygen was the basis for the atomic mass unit at 16, right? Well, it turns out that 1 mole of oxygen atoms weighs 16 grams. And so 1 mole of hydrogen atoms weighs 1 gram, etc. So the mole gives us a proportionality constant between the mass of an atom in atomic mass units and in grams. So when we want to talk about single atoms, we use the atomic mass unit. And when we want to talk about atoms in real-world quantities that we might hold in our hands, we can talk about their masses in grams per mole. In short, it gives us a way to take a measurement that we can take in a lab, like grams of a substance, and convert it into a number of atoms or molecules. This famous number, 6.02 times 10 to the 23rd, is commonly called Avogadro's number in honor of Amedeo Avogadro, who's often credited with first proposing the existence of such a proportionality, although he himself did not discover it. This very famous chemical unit, the mole, has gained something of a celebrity status among chemists, many of whom actually celebrate a tongue-in-cheek holiday each October 23rd, 1023, affectionately referred to as Mole Day. Temperature is, of course, a measure of how hot or cold an object is. We're all accustomed to this kind of measurement. We check the news or the internet most mornings to find out just how hot or cold the air temperature might be on a given day. These temperature predictions are always reported in degrees Fahrenheit or degrees centigrade, very useful units since the values upon which they are based are temperatures with which most of us are familiar. Early temperature measurements were conducted using the Fahrenheit scale, developed by German physicist Daniel Gabriel Fahrenheit in 1724. On Fahrenheit's scale, water freezes at 32 degrees and boils at 212 degrees. Now, the exact references that he used to create his scale are actually a bit unclear, but it's generally presumed that he used the lowest obtainable freezing temperature of seawater as his reference point for 0, and the human body temperature as his reference for 100. In 1742, however, Swedish physicist Anders Celsius proposed a slightly more systematic scale, using pure water as his reference material for both of these points, defining 0 degrees as the freezing point of pure water and the boiling point of pure water as 100. We often refer to his system as centigrade, indicating his 100-degree scale between references. Since each of these terms, Celsius and centigrade, both begin with the letter C, they have come to be used interchangeably. This was a more logical and rational approach to temperature, but still based itself on that sliver of conditions that we most often experience here on Earth. Both of those scales are fine for weather forecasting or a quick physical check from the doctor. But temperatures that we experience here on the surface of the Earth represent just a tiny fraction of the temperature conditions that the entire universe has to offer. It would be a bit arrogant of us as a species to think that our small window on temperature conditions is really the best way for us to set a standard for temperature as cold as deep space or as hot as the surface of the sun. To a chemist, temperature is not a way to decide what jacket to wear on a given day, though we still check the weather forecast before leaving home. More than that, though, it's a measure of the energy of molecular motion in a system. It tells us how rapidly atoms and molecules move, collide, and even vibrate, twist and tumble. And this can help us to understand why they behave the way that they do. But if we want to explain how atoms and molecules behave throughout the universe, we have to consider all relevant temperatures that we might encounter, from the frigid conditions on the dark side of the moon to the scorching center of a pulsar at the edge of the universe. And that requires us to rethink temperature a bit. We'll need a scale of temperature that truly allows us to compare the atomic and molecular motions within any systems that we might encounter. It was nearly 100 years after Celsius that temperature scales got another upgrade. This time from Lord William Thomson Kelvin, who proposed a new temperature standard. See, in Kelvin's time, it had been realized that atoms and molecules can move and collide. Their bonds can vibrate. these molecular motions are essentially temperature. The colder a sample gets, the slower the molecules and processes within it become. And Kelvin wanted a temperature scale that directly communicated how vigorous these motions were in different samples. Kelvin suggested that the zero reference of the centigrade temperature scale should be not the freezing point of water, but 273 degrees below that, the temperature at which all molecular motion stops. This scale, in which the entire Celsius scale is offset by 273 degrees, is called the Kelvin scale. We call the Kelvin scale an absolute temperature scale because 0 kelvins means no molecular motion, and you can't move slower than not moving. Now, measuring temperature in units of Kelvin has some very important advantages that we're going to explore in multiple lectures as we begin to investigate how temperature affects the properties of matter. It may not be apparent just yet, but mark my words, kelvins are an indispensable unit of temperature in the science of chemistry. We just finished reviewing a few units used by chemists to convey simple properties like length, mass, quantity, and temperature in chemistry. So we now have the skills needed to convey these properties simply to other chemists. But that only allows us to answer a few simple questions. Questions like, how many miles, or how massive is a helium atom? You had to know that this was going to come up eventually. Math. Whether it gets you excited or it makes you cringe, mathematics is how we make sense of the universe. And calculations are a critical part of exploring the world at the molecular and atomic level. So we're going to have to spend a little bit of time on this subject before we go too far. I'm going to be assuming that you're familiar with fundamental mathematical concepts like multiplication and division, logarithms and exponents, as well as just a hint of basic calculus. If so, then you have all the math background needed to get through this course. Now, to answer questions like those that we asked previously, we need to be able to convert one unit into another, right? Sometimes that math of chemistry can seem a little bit overwhelming to the uninitiated. But we have a special trick that helps us internally check any equations that we set up. And it's tied to today's discussion about the difference between a number and a value. It's the inclusion of units in a calculation. So let's begin our discussion about how unit conversion factors work, using an equality that's probably a little bit simple. In fact, it's really a little bit simple. X equals X. Now, why would I put something so simple on the screen? Because remember, we just talked about the difference between a number and a value. And in this case, I'm talking about values. So any two values that are equivalent to one another can be thought of as my white X and my yellow X in this case. But values do behave a lot like numbers when we use them in mathematical operations. So in this case, one value over another equal value can be thought of as being equal to 1. Remember, we have to carry our units along with it for this to be true. Now, let's look at another very simple mathematical operation, the identity of multiplication. The identity rule says any value times 1 is just equal to that same value. So when I multiply any value by 1, or something that has two equal parts in its numerator and denominator, I get the same value. And because of my first equality, I can substitute that x over x into the equation. In other words, as long as what I'm multiplying by has a numerator and denominator that are equal values, I don't change the value of the equation, and therefore I can relate one to the other. For example, 1,000 grams equals 1 kilogram. Well, that means that I can multiply anything I want to by 1,000 grams over a kilogram without changing it. Now, the units might change, but I won't be changing the value. The same is true for, say, 3,600 seconds in an hour. How about 1 mole being 6.02 times 10 to the 23rd? Or even 1 mile equaling 1.6 kilometers. Any relationship that involves two equal quantities or two equal values can be done this way. And of course, I can flip these over because the reciprocal of 1 is 1. Which means all of these are also considered equalities when I'm thinking about values. What that means is I can multiply anything by these conversion factors and not ultimately change what that value really means. only change the unit in which it's expressed. So let's take a look at how we can use this to set up an equation. Let's answer a fairly simple question. How many grams are in 2.5 pounds? Well, let's start at the beginning. We know we have 2.5 pounds. We want to know how many grams are in that 2.5 pounds. So we've already defined our starting point and we've defined our goal. Since our goal in this equation is to eliminate the unit of pounds and add in the unit of grams, we're going to have to find some kind of equality or set of equalities that allows us to navigate that unit transition. So having defined where I want to begin and where I need to end, I can create my unit conversion factor using an equality. In this case, I'm going to use the equality 454 grams is equal to a pound. So if I place 454 grams over 1 pound and create a new factor for my equation, I can use this without changing what my equation represents, which is 2.5 pounds. I'm going to place that conversion factor into my equation, and before I do the math, I'm going to use the units as an internal check to be sure that I've set it up correctly. Pounds appear in both the numerator and the denominator of my new mathematical equation, so they're going to cancel out just like any other unit would. Grams, however, do not cancel out in the equation. They're only present here in the numerator, which means when I run this equation, I'm going to get an answer in units of grams. So my unit analysis has confirmed that my equation is set up correctly. Now I'm ready to grab a calculator and do the math. And I can determine that there are 1,135 grams in 2.5 pounds. They are equal values. And this doesn't stop just at converting units. They also extend to a number of physical constants and other types of equalities that we can find in nature. One example of this is what we call the molar mass of an element or molecule. For example, 1 mole of carbon is equal to 12 grams of carbon, which means that I can create conversion factors of 1 mole per 12 grams carbon and also 12 grams per 1 mole of carbon. So if I need to convert grams of carbon to moles of carbon or moles of carbon to grams of carbon, I have a usable unit here that I can insert into my equation, which will give me exactly what I want without changing the value. Similarly, we can use things like density. 2.27 grams of the most common form of carbon, graphite, is equal to 1 milliliter of graphite. So I can create a density value of 2.27 grams per milliliter. Similarly, if it suits my needs, I can create a conversion factor that's 1 milliliter over 2.27 grams. Because those numbers are equal, I can put either one on the top or the bottom of my conversion factor and still have a factor that won't change the value in the equation that it's inserted into. So all of these are treated as though they were equal to 1. Now let's take a look at how we can use some of these factors to solve slightly more complex problems than just converting units. How about this? Water has a molar mass of 18 grams per mole. So a mole of water molecules weighs 18 grams. Now the density of water is 1.0 grams per milliliter. And we'd like to know how many milliliters will be occupied by 3 moles of water. Well, again, we're going to start with what we know. 3 moles of water. We're going to ask ourselves, what's the goal? To calculate the number of milliliters of water. And now I have to find those conversion factors which will help me to cancel out moles of water and give me milliliters of water. So let's begin by creating some conversion factors. We know from our problem here that 1 mole of water weighs 18 grams. So there are 2 potential unit conversion factors I can create. 18 grams per mole or 1 mole per 18 grams. So which one of these do you think we're going to place into our equation to get ourselves closer to the goal of canceling moles of water and getting milliliters? Well, obviously, we're going to use the one that has moles of water in the denominator, right? Because when we do this, notice that moles of water are going to cancel. But if I run the calculation as is, It's going to tell me how many grams are in that 3 moles. And I want to know how many milliliters there are. So I need another conversion factor. So let's look for our second conversion factor that will fix this problem. Okay, we've got 1 gram of water equals 1 milliliter of water. We know this as well from our problem. So this opens up 2 more unit conversion factors that we might potentially use. That would be 1 gram per milliliter or 1 milliliter per gram. Now in this case, mathematically it won't make a difference, but to be absolutely thorough, we need to be sure we choose the correct one of these conversion factors. So which one do you think it will be? Right, of course, we need to use the one where grams of water is in the denominator so that it will cancel with the grams of water in the numerator of my expression. So when I place that into my equation and conduct my unit analysis, I see that grams of water cancel. Now my equation on the left side will produce the desired units on the right-hand side. It's time to do the math. Grab a calculator and determine exactly how many milliliters of water are in that sample. And of course, we put that into our calculators. We get 54 milliliters of water. This is the volume that 3 moles will contain. So let's review what we've covered in this lecture. We started by considering how chemists deal with dramatically large and small numbers in measurement. How one solution is to convert them into scientific notation, and another solution is to modify standard units using metric prefixes, like the nanometer. Next, we took a look at a third solution to measuring a few of the most basic properties of matter that chemists need to understand. We explored some brand new units, custom-made for measuring atoms and molecules. We started with length and mass, 2 measurements that are so small in atoms that they defy conventional units like meters and feet or pounds and kilograms. Instead, we saw how the angstrom has become the preferred unit of measurement for lengths because it results in small, manageable numbers when applied on the scale of an atom's radius. Then we thought about mass and how the stunningly small size of an atom also means that atoms have masses far too small to determine by weight. So chemists resorted to a new unit, the atomic mass unit, based on the simplest whole number ratio of masses between oxygen and hydrogen. We discussed counting atoms and molecules and how it's ill-advised to do so on the scale of a human lifetime. Instead, we saw how a hypothesis proposed by Avogadro ultimately led to a new counting unit called the mole, and how this quantity represents the number of atoms of a given element needed to comprise a mass in grams equal to that element's own atomic mass. Then we gave some thought to temperature and how chemists think about this critical property in terms of molecular motion, ultimately prompting Lord Kelvin to calculate an absolute zero at which all molecular motion should stop. We saw how we use this so-called absolute zero as a benchmark in the Kelvin scale of temperature. Finally, we discussed how the units of a particular value can be converted and interchanged by treating their units like factors in an equation, a tool that we will return to again and again as we go forward. Now that we're masters of measurement on the scale of atoms and molecules, we have one more basic skill set to acquire before we can begin probing the structure of the atom. We're ready to take a look at one of the most commonly used tools for measuring chemical phenomena. We're going to spend our next lecture getting familiar with the chemist's perspective on light.